So let's start. So welcome everyone to the second week of this program. We are very glad to have Yara here as our first speaker for this week. He's also the person who's most responsible for bringing this program together. So thank you, Yara, and look forward to your talk.
Okay, thank you, Suvrat. Yeah, welcome to the second week of the program. So I will give a talk, or the two lectures on loop Amplituhedron and some of the more recent work. But I will probably start more slowly with kind of introducing kinematical variables we will work with, and then some ingredients that will eventually lead to this geometric construction. So you heard some of the things that I will talk about already from Johannes on the side of amplitudes, and then also in the lectures by Melissa on the Amplituhedron. But I will really focus on loops here rather than the tree level, which is the thing that she was talking about. So I will kind of slowly go in and we will see how far we get this lecture, and then we will finish the next lecture. So despite the kind of the title I put was the Amplituhedron for IR finite quantity. We will talk also a little bit about IR divergences or IR finiteness, something that Johannes was also discussing partially in his lectures. And so this will be a motivation where we would like to go, but we will do it in several steps. We will start with talking about the loop integrand as the main object of our interest. We will talk about momentum twisters and momentum twister geometry. And then about the loop amplituhedron, and then about some more recent work about the refinement of the loop amplituhedron to some IR finite object, which is certain Wilson loop. And we will end with some new type of expansion for this object, and which is also related to the amplitude, as we will see. And it provides certain window into all loop order resummation. Not for the entire amplitude, this is very difficult to do, but you will see there is some certain geometric hierarchy of objects that contribute, which goes in parallel with the loop order, and we will be able to say something non-perturbatively, in certain approximation. Okay, so this is the plan. We will stick with our favorite theory, which is planar n equals 4 super Young-Mills. So both lectures will be just about that. Some of the ingredients here are also relevant in other theories. The loop integrand is something which we can talk about in any planar theory. For non-planar, there is a subtlety. The momentum twisters is closely related to that, and that can be also used for any planar theory. This is, of course, very specific for n equals 4 super Young-Mills. But some of the objects, some of the building blocks that we will discuss could be potentially relevant in other theories once the construction in other theories exists. Okay, so let me start with just talking about the loop integrand. Now, in general terms, so typically in quantum field theory, when we calculate loop amplitudes, the loop integrand is just some intermediate object in the calculation. Yeah? So the traditionally, or the standard way how to think about it, you take the amplitude, you express it in terms of some building blocks, let's say Feynman diagrams in a usual way. Now here we more specifically talk about loops. So depending on the loop order, the process, and so on, you have a bunch of diagrams. And they involve some internal loop momenta that you are supposed to integrate over. So there is a diagram, and there is some integral in, well, let's say in d dimensions, but here we stick to the four-dimensional case. And we should integrate, and this is some rational function that you get from Feynman rules. And this is kind of a standard way how to think about it. So this function as the rational function of the loop momenta k, and external momenta doesn't have any kind of deep meaning. Also, depending on the gauge, there are many ways how to write these objects, yeah, and so on. Also, what the loop momentum means might be, it's just your choice, depending how you choose k. You get different rational functions. Once you integrate, it doesn't depend how you chose it, and so on. However, there is in planar theories, there is a meaning in which we can basically flip the sum and the integral and sum all of the Feynman diagrams or all the objects which contribute prior to the integration. Yeah, and basically write it as an integral of some rational function which depends on the loop momenta, maybe many of the loop momentas, L in general, and then you integrate over them. Okay, and this is the loop integrand. Okay, so now as we will see, it's very important that it's planar theory to do that. Johannes also briefly discussed that in his lecture, because in planar theories we can basically assign globally what does the loop momentum mean. We can say what the loop momentum means in different diagrams, and therefore we can line them up and we can sum them prior to integration. And the best way how to do it is through the dual momenta, and then we will eventually use these momentum twisters for that. In non-planar theories, you can in principle do it, but at the moment there is no reasonable way in which the object that you are getting on after the sum makes any sense, because you can choose your k differently and there is no canonical way how to do it. Now, there is some progress in giving sense of the non-planar loop integrand, but it's not directly related to the assignment of the loop momenta to diagrams. Yeah, maybe you heard about Nima's proposal of the surfaceology, when a very important ingredient is the 1/n expansion, that you kind of draw the diagrams on different surfaces, and at each surface you can make sense of the loop integrand. Yeah, but if you try to do it for gravity, it would be problematic. So definitely there is an interesting progress for the non-planar loop integrand. But in the momentum space, if you want to stick in the momentum space, we have the planar integrand is the object which makes sense for us. Yeah, just to kind of illustrate the subtlety for that. So assignment of the loop momentum. So if we have planar, so I just giving some example. Yeah, let's say we look at some planar two-loop amplitude. Yeah, the planar means that there is some canonical ordering assigned to it. Yeah, planar in a sense that if we talk, for example, about Young-Mills amplitude, there is some group structure. We do large n expansion where the leading order only the canonical ordering of your external momenta. So all the diagrams can be drawn on the disk actually contribute. So if we look at some planar amplitude, let's say a two-loop to kind of make the point more visible, there will be contributions, let's say, of these two diagrams. And you would have two loop momenta to assign. What is your loop momentum 1 and 2, some k1 and k2. And these dual variables that we will talk about also, and then momentum twisters just do it for you. Yeah. So, for example, K1 lives here. And in the other diagram, it will be between 1 and 2. K1 would be here. Yeah, so this is alignment of K1 in both of the diagrams. And let's say K2 was here, and K2 would be between 1 and 2. There is no such a propagator here, so we would have to say that this propagator is K1 minus T1, where P is the external momentum. It will be kind of more clear, the assignment, once we work with these dual variables, but we can also do it just in original momentum. While if we have a non-planar amplitude, nothing like that is possible. So in addition to this planar diagram that would contribute, we would have also very deeply non-planar diagram. And even if we start with assignment, the loop momentum K1 here, there is no canonical way how to say that the same momentum K1 is in the other non-planar diagram. Okay, so this is at a very practical level. Of course, this is rooted in these variables, which make that manifest, which require planarity, they require ordering. But you can even kind of understand it directly in the momentum space, that once you use planarity, once you lose the canonical ordering of your diagrams that can be drawn on the disk, you are losing this alignment of different loop momenta in different diagrams. So you cannot perform this summation prior to integration in any reasonable way. So the loop integrand, at least in our way of thinking about it, requires planarity. And because this will be our central object, we have to stick with the planar theories. And we also require this n equals 4 maximal supersymmetry to actually get to this geometric construction. As I said, there are attempts or approaches for the non-planar case. This surface-hedron construction, which gives you non-planar loop integrand, but yeah, that would be a longer story. And the non-planar loop integrand by itself is some infinite object, which kind of requires all possible assigning of loop momenta in the diagrams. There is some modding out by some group that you can make it finite, but in our way of thinking about things, we stick with the planar theories. Okay, very good. Any questions about this point? So now, even having this object, it's not clear that this object has any nice properties, even if we kind of define it in this way. First, if you are just in general planar theory, and you write the amplitude as an integral of this loop integrand that we constructed, the loop integrand is actually not gauge invariant by itself, because depending how you choose the gauge, you get different answers. After the integration, they produce gauge invariant amplitude, but the loop integrand by default is not gauge invariant. So again, there is some ambiguity, some redundancy if you just talk about general planar theory. Let's say pure Yang-Mills theory. Okay. However, as it turns out, in the n equals 4 super Yang-Mills, there is actually a unique integrand, which satisfies certain additional properties that we require. So there will be a unique object we will talk about. Yeah. So this is also one of the main reasons why we need this maximal supersymmetry to actually make the whole construction go through. It doesn't mean that, let's say, pure Young-Mills integrand is meaningless, but you have to do more. For example, if you want to find some geometric construction for that. Now, again, in these Nima's recent work, they actually do work with non-supersymmetric integrands. But for that, you have to kind of leave the momentum space. You have to go to more abstract kinematical space, and then you get a unique object. Yeah? But you are not working with with standard momenta anymore. Yeah? You go to this abstract kinematical space, which once you want to reduce it to just the momentum space, you have to make certain choices, and that kind of brings this ambiguity. Yeah. Of course, there might be something preferred, so this is still something to be understood, how it interacts, these objects, with just the standard momentum space. Okay, but in n equals 4 super Young-Mills, in the planar limit, we have one object which is unique loop integrand. Now, why do we even focus on this object and don't just directly talk about amplitudes? Yeah, because this is still something that needs to be integrated. So it's not a final result of any amplitudes calculation. But it's very useful kind of intermediate step. It's very useful object. And as it turns out, once you understand it very properly, it might make even the last step of doing this integration easier. Okay, so let's so loop integrand in planar n equals 4 super Young-Mills. So the one reason, important reason why this is a good object to study is that, after all, this is just a rational function. Yeah? So it's a rational function of external momenta and the loop momenta. So this is true for any loop integrand, but just to point out, this is a rational function, while the amplitude is some complicated transcendental function. Yeah, so the function space is much easier. Yeah, so now the loop integrand depends on many more parameters. Yeah, because the loop amplitude only depends on external momenta. The loop momenta are integrated over. So it's a function of many more parameters than the amplitude itself. Now, while the amplitude in general suffers from divergences, and we have to regulate it, the loop integrand is just a rational function. There are no divergences in the loop integrand. Yeah. Now, in planar n equals 4, the situation with divergences is generally easier. There are no UV divergences, as you heard before. The IR divergences take some particular structure. However, there are IR divergences here. Yeah. So you have to deal with that. You cannot really stick with the 4-dimensional integration. You have to do something with that in order to regulate them, either to go to 4 minus 2 epsilon divergency, the dimension in dim rank, but then you really want to stick with 4, because in 4 dimensions, the theory is properly defined, or you have to do something else. You have to do, going on the Coulomb branch of the theory, you have to do some regularization. While if you just talk about the integrand, none of that is needed. Of course, you would like eventually to go here. So you have to face these questions. What we will do later in this talk, we will not face these questions about divergences, because the object that we will be calculating will be actually IR finite. Yeah. So then the integration just can carried over without addressing the questions of divergences at all. Okay, so let me now talk a little bit about these kinematical variables before we go farther, because they will make our life much easier to actually studying this function. Yeah. So there are kind of several steps. So we will change the variables in steps before we arrive at the momentum twisters. that are most convenient. I can draw all the way. Okay. So okay, but I can go farther. Yeah. So change of variables from momenta. So the first step are so-called spinor-helicity variables. You maybe heard about them before. The spinor-helicity variables make manifest that the particles are massless. So we will work in this theory, all the particles are massless. So instead of talking about momenta, we associate with the momentum P pair of two spinors, lambda, lambda tilde. And this makes manifest that P square is 0. You can think about it in a following way. You can write P in a matrix. And the determinant of this matrix P, this is matrix P, is 0, which means that the P can be written as a product of two vectors, and this is exactly this lambda, lambda tilde. Okay. So the information about the massless momentum P is stored into a pair of two spinors. But this is true in general for any massless momenta. That doesn't require planarity or anything. Yeah. Then we have these dual variables. That's another ingredient. So the dual variables are inspired by. So let me just show it first on some diagram. Okay, well, let me start with the definition. So instead of one momentum pi, we write it as a difference of two other vectors. Instead of vector p, two other vectors x. It's a difference of xi plus 1 minus xi. And this, what this makes manifest is that if we sum all momenta, we get 0. Obviously, writing in that way makes manifest that if we sum over all momenta, we get 0. Okay? Now, these two conditions, the sum of momenta being 0 and the momentum being on shell, is exactly which is obstructed in the usual momentum definition. Because your momenta are just subject to both of these constraints, which makes the analysis much harder. Yeah? So the spinor-helicity variables trivialize this one, while the dual variables trivialize that one. And the momentum twisters will do both at the same time, eventually. Okay? But first, these dual variables are often useful. They are kind of the first step towards these momentum twisters, because these are the variables which associate momenta with faces of the diagram instead of edges. So normally, when we talk about momenta, either internal or external, they are associated with edges. Right? There is this loop momentum K, there is something flowing in the diagram, it's K plus P1, and so on. So the momenta are naturally associated with edges, but these dual variables are associated with faces. So there will be actually some variable y that is loop variable, the dual variable. And the external variables will be x, this would be x4, x3, x1, x2, x3. And the difference between them, you just kind of connect these two dots, is exactly the flow in that edge, which connects these two faces. And that is this relation for the external momenta. And for the loop momenta, we would have k here from the picture would be y minus x4. Okay, does that make any sense? So instead of talking about variables associated with edges, we now associate variables with faces. These are the dual variables. Okay. But the last step is to go from these dual variables to momentum twisters. So this definition of these dual variables, we can also nicely we can nicely view it as some polygon when the vertices are these dual variables. And the edges are the momenta. And this is the definition of how to go from, well, association, which momentum corresponds to which edges. So the pi, the p1 is the momentum which goes from vertex x1 to x2. This would be p2, p3, p4, p5, and p6. Okay. So here the +1 is always meant modulo cyclic. So if we have 6-point amplitude, x7 is the same as x1. Just wraps around. So here from this picture, it is clear that if I start with some 6 points x with some kind of coordinates, then I connect these momenta, then the momentum is conserved. The momentum is conserved is just a statement about that the polygon closes. Yeah? So the sum of pi here is obviously 0. Okay, now we go from here to momentum twisters. So we will have a similar polygon. And then the momentum twisters lie in a different space. So we can think them about the coordinates on some projective space P3. So these are 4-component objects. And the association between these variables and this variable is following. So the momentum twister, so I is that index in P3. In the first 2 slots, we have lambda, and in the next 2 slots, there is a dot product with x, I, or one of these, to put I, to put it here, I and lambda again. You basically, you sum over this index A. So, but geometrically, you associate a point in this dual space with a line in the momentum twister space. So x1 goes to the line z1, z2. Yeah, so it's not point to point, it's just not taking this x and going to z, but you can also see from this definition that the z doesn't only depend on lambda or lambda tilde of particle with the same index, but also on this x, but the x is connected to 2 adjacent, two momenta, not just a single momentum. Okay, so in this momentum twister space, we have n points z, and we can, for each point x, we have a line. Now, because the momenta are massless, these x's are now separated, then the adjacent axes, x1 and x2, share the same point. So therefore, we are getting this closed polygon. Yeah? So the x1 is associated with z1, z2, and x2 point would be associated with z2, z3. It will have the same z2. Okay? So the vector in space-time is associated with the line here in momentum twistor space. Here, despite we change the variables from p to x, we are just still talking about the same space-time. Yeah? But here we are in a different space. We are in some projective space P3. Now, there is a question of is that real space or complex space? We discuss it a little bit later, but in general, because we will talk about the loop integrand here, it's useful to take all variables to be complex a priori, have no restriction, and then these z's are also complex. Now, if you restrict yourselves to the real momenta, these momentum twistors are still complex. So the reality here doesn't translate to reality here. Yeah? This is then subtle when we actually would like to do the loop integration, because now the reality is important. Yeah? As long as we talk about tree-level amplitudes of loop integrands, these are rational functions, no branch cuts. It doesn't matter if it is real or complex a priori. But once we talk about then the loop integration, the reality is important. And then the contour that we will be associated in the momentum twistor space is some complex contour, which is not completely understood how you do the integration over. Okay. But so far for us, everything is complex a priori. Yeah, we don't do any restriction to the real space. So, so let me here kind of end this kinematic variable discussion. So integrand in momentum twistor space. And you will see just in a second, while this is useful, apart that eventually the Amplituhedron construction works in the momentum twistor space, this is where it's defined. Despite, we can also just stick with the spinor-helicity space and define the geometric space also there, which corresponds to the momentum Amplituhedron. But you will see how some manipulations just with the integrand before even going to any geometry is very convenient in these kinematical variables. So we start, the data are for n-point scattering amplitude. We talk about the integrand of that amplitude. So it will depend on n momentum twistors. Zi. You can go between Zi and the original momenta. And then, as I also alluded to, in the end, the point in space-time is related to a line in momentum twistor space. So the loop momentum is associated with a line, not with a point. Yeah. So loop momentum, loop momenta are lines in momentum twistor space. And we denote these lines AB with index I, just denoting which loop line we have in mind. In some simple cases, like one loop, two loop, three loop, people often use A, B, C, D, E, F, just to avoid indices. Yeah. So the loop momentum is associated with line, so it doesn't matter which 2 points we choose on a line. This is just our choice. It's the line itself. Yeah, this is how we denote it. Now, the momenta, just the external momenta, are also associated with lines, but these lines intersect. So in the end, we don't get two n variables, but only n variables. Yeah, so we can directly just talk about the point Z, despite the conversion from the original momenta again goes through these lines. But the loop momenta are not, these loop momenta are not on shell. So these are just off-shell loop momenta. So therefore, each of them has its own line. And also the counting of degrees of freedom works if you do it more properly. In momentum twistor space, the line has 4 degrees of freedom, which is exactly 4 degrees of freedom. And loop momentum in just the momentum space. And here we end up in the same number of degrees of freedom for just external momenta, but then it's more complicated because there is momentum conservation. So you have to do the counting a little more properly. Okay, so in the end, our loop integrand is some rational function of the Zi and these loop lines A, B, J. Yeah, so it depends on that. And now it doesn't depend on it in some arbitrary way. So yeah, we will talk more about it. Sorry? Yeah, so it corresponds to a line. So you can choose any points on that line. A and B are arbitrary points along the line. Yeah? But yeah, so if you want, the individual twistors have some index I, it's some SU4 index, and the line is like a bitwister. Yeah, so yeah, so it has 2 indices, the line AB. And it's antisymmetric in that, so you kind of antisymmetrize in these indices. Okay. So now going just from these variables to some invariants. So in the momentum space, we have Lorentz invariants like L square, P1 plus P2 square, just the standard Mandelstam's. So what is the analog of that in the momentum twistor space? So the basic object is a 4 bracket because these momentum twistors have this twistor index I, and this is it has 4 components. It's a 4-component vector, the twistor is. So what we can do is just to contract all these indices, but we need 4 of them. Yeah. So the basic object is 4 bracket. If I use the external the twistors 1, 2, 3, 4 as the labels, this is an epsilon A, B, C, D, and just a contraction of these indices. Okay. In other words, this is also the 4x4 determinant of just taking the 4 twistors and build a 4x4 matrix, take the determinant of that. Okay, so this is a basic object. You can put these external twistors as arguments, but you can also use these loop lines. So you have A, B, 1, 2. The A, B always goes together because the loop momentum depends only on that line, not on individual A and B separately. And yeah, this will be again 4x4 determinant with taking the line AB and Z1, Z2. Okay, and so on. You can also do a 4 bracket A, B, C, D. So as I said, if we are at low loop orders, then we often use these labels. So you have 2. This would be, again, the 4x4 determinant of the momentum twistors like that. But it's important that in order for the whole expression to make sense, everything must, in the end, only depend on a line AB, not on individual points. Somehow, there are kind of spurious things that the expression might seem that it depends on A and B separately, but in the end, it must depend on just a line. Yeah. Otherwise, you are not describing the loop momentum. Otherwise, you are just describing some other variables. Okay? So these objects will enter our expression. So our I will depend on this type of objects. We will do some examples to see how it looks explicitly. So let's just do it for some integrals, some simple integrals that would be more familiar. Yeah, sure. Yeah. So you can do it sometimes in other dimensions. You can do it in 3 and in 6. But yeah, in general, you cannot do it in D dimensions, like D.
Yeah, the title of this talk is about IR safe quantities.
Yes.
The question is, if you wanted to do it in general, you might want it in 4 minus epsilon.
Right, so you cannot do that. Yes, yeah, because it's really the momentum twisters, it's like a discrete. Yeah, you need an integer number. And in principle, you can do these things in higher dimensions, in arbitrary D, but then you are not really describing amplitudes. Yeah, just formally, you can kind of do these things, but in order to overlap with what you would do in the momentum space, yeah, you have to have special D in D equals 4. So maybe one important thing I didn't say, these Z's are completely unconstrained. So that's basically the main point here, the main advantage. So I should have emphasized it. So you gave me just n momentum twisters, and if you translate it back, it corresponds to n momenta which satisfy momentum conservation and are on shell. Yeah, there is no constraints on the Z. So that's basically the most important, like, kind of, why do we introduce them in the first place? We removed all constraints. If you do it in other number of dimensions, the Z's would be constrained. They would still be useful for other things because these Z's make some symmetries manifest. Yeah, so this dual conformal symmetry Johannes also discussed, right? Then this is manifest in these momentum twisters, while it's more obscure in just momentum space. Yeah, so these are also useful in other dimensions. In 4 dimensions, they are unconstrained, which is like extremely important. But you cannot really do it in 4 minus 2 epsilon dimensions, yeah, because you live in this projective space, and unless you make some sense in living in 3 minus 2 epsilon kind of projective space, yeah. You really need this discrete thing. Therefore, if you build this integrand for the amplitude, which is IR divergent, you cannot really use DIMREC directly for that. You cannot use DIMREC in momentum twister space. You have to do something else. And one thing to do historically, which Johannes found with his collaborators a number of years ago, is basically, but this is now specific for n equals 4 superangles, to go on the Coulomb branch. And that can be done nicely in the momentum twister space, and then these amplitudes will be IR finite. Yeah. But as just the general scheme, you have to find some other regularization than DIMREC. Very good. Okay, so let me give some simple example. So let's say we have a box integral. So how you would write the box integral? Now we are not even talking about amplitude, despite the box integral itself is a 1-loop 4-point amplitude in planar n equals 4 superangles. So the single integral is the full amplitude in this theory. Yeah, but so we know how we would do it in just momentum space. We would have 4 propagators, and the denominator corresponds to these 4 lines. And then we would have some numerator there. Actually, in planar n equals 4, the only relevant thing is the numerator, which is just a constant, doesn't depend on the loop momenta, it's just a scalar box. And to read it off, what is in the momentum twister space without doing through this translation that we discussed here, is that this propagator corresponds to a 4 bracket AB12. So AB lives here. This is a line, so this is also like a phase 1, 2. This is phase 2, 3, 3, 4, and 1, 4. So it shares a lot of the spirit with these dual momenta. When you cared about the phases, here it's also associated with phases. And this propagator is just AB12. This propagator is AB23. This is AB34. And this is AB14. Now, in order that to be a scalar integral, the whole thing must be projective in all of the z's. Yeah? So there is projectivity. So if we rescale any z by tz, the integrand should be a weight 0. So now there is some measure I will specify just in a bit. It's like the d4L measure in the loop momentum space. So in the momentum twister, there is some measure. And the measure eats up 4 of the weights in each A and B. So the numerator does not depend on AB. And so you have only these external z's to cook up the right weights. And the only thing that you can do is the 1, 2, 3, 4 square. Yeah, you can write a 1, 2, 3, 4 in different order, but you are dealing with a determinant, which is antisymmetric in all labels. So this is it. So the integrand for that, or the box written in the momentum twister space is that. Yeah, here maybe I should specify the measure, but this is kind of less interesting. As I said, it's an analog of the D4L. But just for completeness, D4K, I use K here for the loop momenta. So there is some measure AB D square A, AB D square B. Yeah, here it's kind of, you are integrating over A and B, but everything just depends on the line. This is the right measure. And you see that this integrand is projective in all of the z's. So it doesn't carry any weights. If it did, the integral wouldn't be scalar because the weights from z comes from weights in these spinor helicity variables. Yeah, so there would be some weights from lambdas, which we are here talking about just the scalar integral. So this is actually equal to d4k st. This would be the right normalization of some k square, k plus p1 square, k plus p1 plus p2 square, k minus p4 square. So we could also start with this and do the translation. We would land up on that, but there is a much more easier kind of mnemotechnic rule how to read the integrand directly from the picture. Okay, very good. So let's do just one more example, just to be more familiar now with these objects. So at 2 loop, we have 2 of the loops, so I denote them A, B, and C, D. Now the integrand will have 7 objects in the denominator, 7 propagators. So here was 4 propagators at 1 loop. We will have 7 here at 2 loop from this diagram. And you can directly read out what they are. So AB talks to 1, 4, then to 1, 2, then to 2, 3, CD 2, 3, CD 3, 4, CD 1, 4. And then there is also this internal propagator between the loops. This is ABCD. This is like analog of K1 minus K2 square in the loop momentum space. And now there is a measure in AB, measure in CD. We can see that both in A, B, and CD, the weights are completely eaten up by the measure. So the numerator is again just some power of 1, 2, 3, 4. And it's actually, the right power is cubed here, if you just look at the weights. Okay, so I just wanted to say here that if you give me some integrand, there is easy to write it in the momentum twister space, unless there is some non-trivial numerator, which I will show just in a second. And these numerators, the very natural ones, are actually much easier to write in this momentum twister space than in momentum space. We will see it, yeah, just in a bit. Yeah. Yeah. So So you need some measure. So okay, so let's think about it like this. Yeah. So if you have an integrand in momenta, you want to integrate over all points L or K. Sorry, the loop momenta K. And the measure on the configuration space of all loop momenta is just d4k. Yeah, you don't have anything else. Here, what we want to do is to integrate over all configurations of lines AB and CD. Yeah, so the configuration space of these lines. And yeah, and this is the right measure for the configuration of all the lines AB and CD. Yeah, so this is the right object with the right weights. Yeah. So here we have two lines. So we have two measures for A, B, and CD separately. Yeah, because we have to integrate over configurations of both of the lines, A, B, and CD. So we have two pairs. Yeah, or what do you? I think the question is okay, yeah, so yeah, I just said it's like analog. So this is exactly d mu AB. Yeah, this is what I meant. Yeah, okay. Right, yeah, I didn't introduce the d mu before, yeah. So the d mu CD would be just the same thing with CD. CD d square C, CD d square D. I will then show explicitly how to calculate with that once we do an example. Actually, once we then go to Amplituhedron and do an example, yeah, I will show it later. Okay, very good. Now, it wasn't completely automatic that this scalar integral can be written in the momentum twistor space as something which only depends on these four brackets. Yeah. This is actually already a consequence of the dual conformal symmetry. Yeah, the dual conformal symmetry tells us that the object, that the integrand, is written in terms of these four brackets with only the only objects that we contract are these Zi or these loop lines ABJ. Yeah. Once you can do it like that, then the object is dual conformal invariant. Now, we can use these planar variables for any other object, not just something which is dual conformal invariant, which happens to be also these two integrals separately. So I used kind of special examples. But you can also have a different integral, which is, for example, triangle integral. So let's look at this. So we can do the same translation. We will immediately run into a problem, which, of course, has a resolution. So if you just write the propagators, it has this integral has three propagators: AB14, AB12, and AB23. And then there is, of course, a measure d mu AB. But now you see that there is a problem because we needed four propagators only to satisfy the right weights in A and B, to just be a loop integral, yeah, without any further statements. We are missing one propagator in the denominator. Now, if we just do it in the momentum space, we can just write d4L or d4k or ddk over any number of propagators we want. There is no restriction. But here we have a restriction because the whole thing has to be projective. So we have actually one propagator missing in the denominator. But the diagram didn't have any more propagators. So in fact, when you write this diagram in the momentum twistor space, there is one more propagator, which I denote as ABI. The AI is something called infinity twistor. and it's some constant object. Yeah, it's just some constant twister. And it's the object which would break this dual conformal symmetry. But then if we, but now we can write this integral in the momentum twister space. So in order to get the right weights, in the numerator, we have 1, 2, 3, 4 bracket, and this I, we have to also have the right weights in I, 1, 2, which is the stuff which is remaining. Okay? Now, what is this I? Let me just say that, as I said, it's some constant object. So it's, if you have some preferred direction, then this integral would explicitly depend on it. And if you have a 4 bracket, which has this I, and then some other 2 labels, from the 4 bracket, it gives you a 2 bracket in lambdas. So this is just a contraction of 2 lambda spinors. So this object breaks this dual conformal symmetry. Okay? And that's correct because the triangle integral is not dual conformal invariant. So it has this explicit dependence on I. Now, the point about, so this translation between momentum space and momentum twisters can be done for any planar object. The only thing that we need is this planarity, the ordering of external momenta.
I have a question. Introducing this infinity twister, is it the same as doing the diagram in position space and taking one point to infinity? In fact, there was a talk last
yeah, maybe you already discussed
that.
Yeah, so it's exactly that. It's exactly that. Yeah, doing this in the momentum twister space. Now, the integrand in planar n equals 4 super Yang-Mills does not depend on the infinity twister. So it's dual conformal invariant, so this infinity twister never appears. If we translated some other integrand, then it will have disappearance. Yeah. So the appearance of this infinity twister is exactly closely related to this dual conformal symmetry. Exactly, its consequence. Okay, good. So now we at least some partial experience with what these integrands in momentum twister space are and how would they look like. Any more questions on this? So let me now, yes. Yeah, it's ABDADA. I will, let's postpone that question a little bit later when we talk about the Amplituhedron. We will start with some parametric space and then we rewrite it like that. So it will be more visible, but yeah, it's ABDADA. Yeah, let's postpone it. Yeah, I will show exactly how to manipulate with that measure. Okay, so good. So the general integrand what is the structure? We saw it in these examples, but in general, we have some objects in the denominator, and the objects in the denominator which are associated with propagators have the following form. They look like AB. Okay, maybe I should AB also put some index because we have more loop lines. ABI KK plus 1 because the momenta, the external momenta are associated with this pair KK plus 1. So these are the only objects which can show up in the denominator. We can also have ABI, ABJ, and that's it. And the denominator we can always read off from the diagram. Of course, eventually we will not talk about diagrams, but about the full integrand at once. So it will have all of them in the denominator if we want to construct it. And then there is some numerator. The numerator has these measures, which are kind of trivial. But the numerator has, in principle, also some non-trivial dependence on these ABI and also on the external momentum twisters. Yeah, we saw so far only the examples when the numerator was kind of dumb. Yeah, it was very easy, but in general, it can be more interesting. Okay, maybe I will show, because this is now closely related to the IR. Let's first discuss about IR, and then I will show some more interesting integrands. Yes? At infinity. Planar. You can, but yeah, here we only are restricted to planar. Yeah, because in order to define the momentum twistors at all, we need an ordering of external lines. Yeah, because this was important in this association because we took a point in position space, or here it's momentum space, really, it's this X, and we associate a line with that. So it's needed that we tell what are the neighbors. Yeah, what is Z1 and Z2. Actually, even introducing these dual variables require to tell you what are the neighbors, right? Because it's Pi, like Xi minus Xi plus 1. You have to say what is I and what is I plus 1. So for that, you need an ordering. If you do it in momentum space, you don't need an ordering. Yeah, so therefore, of course, just the ordinary momenta work for non-planar theories as well. Yeah. Okay, good. Yes. You can, but then you kind of, then it depends on how you introduce the ordering. Also, the propagators are just arbitrarily complicated. Yeah, so you can always like introduce ordering, but it's not, it's really just your choice because the diagram like this just has no ordering whatsoever. Yeah, so if you have this diagram, how is it ordered really? The 1 and 2 are not ordered in any way. So you can just introduce momentum twistors. You can say that the ordering is 1, 2, 3, 4. You can do it. But in addition to just having ordering, you also have to associate the loop momentum with phases. And then there is a problem, what does it mean a phase in a non-planar graph? So in planar graph, maybe that's what I didn't say, but also the important ingredient was that there are well-defined phases of planar graphs. You can say this is phase 1, this is phase 2, this is phase 3. But once you talk about non-planar graphs, what is the phase? Or in other words, what is the kind of fundamental cycle of the diagram? Yeah, is it this one or is it the big one? Yeah, because there are 3 cycles in the graph, but there are only 2 loops. In planar, this is an answered question, but in non-planar, there is no answer to that. Yeah. There is no preferred way how to pick these cycles, which corresponds to the phases. Yeah. So yeah, you can do it, but then it's more just a change of variables without any kind of deep meaning. Okay, good. More questions? So, okay, so our general integrand will have this form. We saw some examples when there was no non-trivial numerator, but I will first discuss now cuts of the integrands, because that would lead us to some interesting statements about IR divergences, which would require to introduce some interesting numerators, and it would kind of all fit together. Okay, so let's talk about cuts in momentum twistor space. So I hope the cuts were mentioned last week in some of the talks. No, okay. But, well, okay, so let me just say very generally, but very quickly also, that if we have the integrand, which depends on the loop momenta and these external momenta, of course, we would like to integrate it over Minkowski space and get the answer. But there are other interesting contours that we can consider. Yeah? And these contours don't turn the rational functions into transcendental function, but into another rational, or in general, some algebraic functions. And these contours encircle the poles in the denominator of the graphs. Yeah? So let's say, for our example of the box diagram, we have these propagators, P1, P2, P3, P4. So we have k square, k plus P1 square, k plus P1 plus P2 square, k minus P4 square, St d4k. And what we like to do is to change the contour of integration such that we encircle these poles in the denominator. Yeah? So the contour is when k square is 0, k plus P1 square is 0, this is 0, and this is 0. So this turns into just calculating the residue of that integral. Yeah? So instead of the Minkowski, we basically integrate over some S1 cycles around these poles. So the cuts corresponds to residues. And it's the residue when we send these factors in the denominator to 0. So in general, it looks like solving some quadratic equations. You send k square is 0, this is 0, this is 0, this is 0. This specifies the k completely. And you basically just calculate the residue on that. Yeah? So the cuts corresponds to residues. And the number of residues you can do is limited by the number of integrations that you have. So at one loop, you can at most set 4 propagators to 0 to calculate 4-dimensional residue. Yeah? So this is called leading singularity. This is the maximal residue that you can calculate, maximal dimensional residue that you can calculate for a given integral. Now, why doing these contours, these special contours which encircle the poles and calculating residue is interesting? Because you can learn information about these objects from just taking residues of it and seeing what it gives you. So this is like this is exactly what is used in recursion relations. So it's like doing some sort of Cauchy's formula. Yeah. So you reconstruct functions from residues. That's one way how to think about it. The other thing is that if the properties of this function, of this I function, is fixed by knowing, or it translates into the knowledge of all of the residues of all dimensions of this integrand. Yeah, so you can tell where the function has a vanishing residue, then there is some physical reason for that. You can also tell based on the unitarity, if you calculate certain residues, you get something that you can predict. Yeah, for example, the loop integrand gives you product of 3-level amplitudes. This is so-called unitarity cut. You take the loop integrand and you set 2 propagators to 0, so some k square is 0, and k plus p1 plus p2 square is 0. The loop integrand actually factorizes into product of 2 3-level amplitudes, and so on. So there is a whole story of unitarity methods and generalized unitarity. I don't have time for that because this is a kind of topic of several lectures. Maybe JJ will say something about it in his talks. Okay, so you will so you can wait a little more if you haven't seen it before. Then yeah, there is a lot to say. But we will care about doing it in the momentum twister space and see how it kind of interacts with some nice geometry. So if you haven't seen it, wait for JJ to tell you more in momentum space, but we will now move forward to this momentum twister space. Okay. So let me, so now going to the beginning of the talk, we said we had this, not tension, but these 2 objects we started with, the amplitude and the integrand. We said that the amplitude is the object that we would like to calculate, the integrand seems like an easier object to calculate because it was just a rational function of many more variables. Now, there is a general question if knowing this rational function, which we have much better access to, in principle, we can calculate it, well, optimistically, we can calculate it to all loops or say something to all loops at least. If knowing these properties of this function, if we can predict what happens here on the other side. Yeah, maybe not calculate it directly. That seems either doing this integration or solving some differential equations. Yeah, the function space here is hard. Yeah, but just knowing something here, can you predict properties here? Yeah. Do the properties kind of carry to the other side? Do they translate from here to here? Yeah. So properties of integrand. And the properties of amplitude. So there is a very generic statement, but also not understood in details, is that the cuts of loop integrands corresponds to branch cuts of the amplitude. Yeah. So if you know something about which cuts are zero, non-zero, what the amplitude does on cuts, it tells you about something about calculating branch cuts on the other side of the amplitude. Yeah. This is understood in some examples, but for many point generic amplitudes, there are too many variables. There is a relation, but how exactly it's related is not totally clear. Yeah. Now, one thing which is naively clear, but in details it's again not, is the UV properties. Because just to tell when this object is UV divergent should be encoded in the integrand. And at some level it is encoded. If the integrand doesn't have the right scaling in the loop momentum, it must be UV finite. Yeah? So for example, at this one loop examples, we already discussed the triangle and the box integral. The UV divergences come from the region when the loop momentum is infinite. So if you just look at the box integral, then k goes to infinity, so basically all the external momenta are irrelevant. You get k squared to the 4, and you see just from the scaling that if you integrate it near k goes to infinity, this is finite. So UV finite. You can also see it here. This would be UV finite as well. Yeah, just the powers of k in the denominator is bigger than in the numerator, so it's just power counting finite. And once you go to a bubble, by the way, the bubble you can also translate to the momentum vector space. It's a planar diagram. The difference would be that you will have only 2 propagators in denominator, and you would have a square in this propagator as well. Okay, but this by power counting scales like dk over k, where k goes to infinity. So this is like d log, not d log, log of lambda. So this is UV divergent. And bubble indeed is UV divergent in 4 dimensions. You have to regulate it, let's say also using DIMREG. That causes problems because the DIMREG doesn't care about UV and IR and mixes that together. You have to do some extra work to separate them and so on. However, so you might say, okay, so that it's easy. You just, in order to tell if the amplitude is UV finite or divergent, you just keep track of these scalings at infinity. Unfortunately, this is not the case. So it works in one direction. If the integrand is power counting finite, like these two, then it's finite. But if it is power counting divergent, doesn't mean that the amplitude is divergent, because these integrations can actually integrate to 0 the bad piece. And the piece which has bad scaling can actually integrate to 0. And the divergence is not present in the end. And exactly this thing is a content of the subtleties and the work on the finiteness of n equals 8 supergravity. JJ can also tell you more about, because it's still, Because we know, this is like doing a very side note, but if we are interested in n equals 8 supergravity, we know that the integrand would be power counting divergent. But already going several loops, the power counting divergence did not translate to the UV divergence of the actual amplitude. But what is exactly the resolution to that problem is an open question. Yeah. Okay, so UV, but in n equals 4 super Young-Mills, we don't have any UV. We don't have to worry about it. Yeah. But we have IR. So now going back to something Johannes discussed more extensively are IR divergences. Specifically, we would like to understand if looking at the integrand, doing some cuts or some analysis, can we tell if the amplitude is UV finite or divergent? Okay. And for that, I first have to tell you where does the divergence, the IR divergence, come from the integrand. Okay, so let's start with, again, let's say this box integral. I will kind of go back and forth between momentum and momentum twistor space. Let's first do it in the momentum space. So we label our loop momenta again. So we have this integral. d4k st. By the way, this st normalization is very closely related to these leading singularities, to these kind of maximal residue cuts, because we would like, once you cut as much as possible, which is 4 things here in this integral, you get 1. Yeah, so this st exactly normalizes that residue to be 1. Okay, but for the purpose of these IR divergences. So the IR divergences come from the region of the loop integration when the loop momentum becomes collinear to the external momentum. Yeah, so the region, so this is called collinear region. So the loop momentum k becomes proportional to one of the external momenta. Okay? And in the integrand, you can see it. If there is a residue of the integrand, which produces k to be proportional to pi, it's a non-zero residue, the integral, after integrate, will be divergent. Now, how to see it here? So once start to do cuts, we can first send one of the propagators, k, to be on shell. Yeah? So the first cut is k squared equals 0. And then we continue. We would like to send the second propagator, the one which is adjacent, to be 0. And we would like to make k to be proportional to p1. If we succeed, the integral is IR divergent. Now the k plus 1 square, k plus p1 square, on the support of k squared being 0, so this is now on-shell momentum k, and this was on-shell momentum in the first place. So this is just an invariant of 2 on-shell momenta. And this can be written in terms of the spinor helicity variables. These are now on-shell momenta. This was a loop momentum initially, but now it's on-shell, so just an on-shell momentum. So we can write it as k p1 angle bracket and k p1 square bracket, because now we can use spinor helicity to write both the k and p1 in spinor helicity variables. And we would like to send it 0, but this is a product of 2 things. And the collinear cut, accessing this collinear region in the momentum space, is sending both factors to 0. We send to 0 both this one and this one. And you can see there is a non-zero cut because this factor was there. This factor factorizes into 2, and we can take a residue on both of them. So as a result of this cut, k is actually proportional to p1. This is the collinear region, and because there is nothing in the numerator which would cancel it, then the integral is divergent. Yeah? So by analysis of these cuts, we can see that the integral would be divergent. And there are actually 4 regions of these collinear regions which would cause divergence in the integral. Okay? If we had, okay, I'm nearing the end, but I'm actually at the end of what I wanted to say now. So this is the general rule. Yeah, the collinear regions cause IR divergence, or could cause, unless there is some special treatment. The treatment would be a choice of some special numerator. And these collinear regions come from, at the level of diagrams, or propagators, they come from massless corners. Yeah. So when you have some momentum here. Yeah, so massless corners are dangerous, and they potentially cause IR divergence. So this was very dangerous, but even box integrals which have only one massless corner, that's also divergent, yeah, because this is the collinear region. Yeah, even like the triangle integral is also divergent whenever it's a local statement about the collinear region. So once you see it, it's divergent. This is the same thing is true at the higher loops. We have a bunch of collinear regions here, also divergent. Okay, now there is a separate question about the degree of divergence. That's a more complicated question. Yeah, how much is it divergent in DIMREC? Yeah. Then you have to do much more careful analysis, but just saying if the integral is finite or divergent, you have to, if it has a collinear region, it could be divergent, and then you have just to see, is there a non-zero residue in that collinear region? And if it is, then it's divergent. Okay? So, so now let's just see it, what is in the momentum vector space, and then I end. So what is the translation of this statement in momentum vector space? So in momentum twister space, the statement about cutting things is a statement about the line AB, or many of the lines AB at higher loops, intersecting some other lines, Z1, Z2, Z2, Z3, Z3, Z4, and so on. Yeah? So sending AB1, 2, which is the propagator that we saw before, to 0 is the same thing as geometrically the line AB intersecting the line. Let me skip the Z's and just call it 1, 2. Yeah? They intersect, which means that there is a linear dependence between 1, 2 and AB, which means that this bracket is 0. So geometrically, these two lines just intersect. Yeah? So doing cuts means moving with this line AB in momentum vector space and intersecting a bunch of the other lines. Yeah? Now, we will discuss these cuts later more, but just to make the point about the IR, what does it mean, and end here. What we really did before with the massless corner in the momentum space was sending, so this is IR cut, sending AB1, 2 and AB2, 3 to 0. Okay, well, this would be a corner 2. Yeah, so this is AB. This can be some rest of the diagram. It doesn't matter. Yeah, and we send it this propagator and this propagator to 0. We calculated, we cut it then. Now, as we saw in the momentum space, there were two solutions to that. Because after sending this one factorizes, and we wanted to send both of the factors to 0. And you can see it geometrically, because you have these lines, 1, 2, 3, is representing these lines. And the first cut is line AB intersecting 1, 2. And then we would like the line AB also intersects 2, 3. But if you just think about it, there are two solutions to that. Either AB goes through point 2, and then it cuts both of them, intersects both of them, or it's in a plane 1, 2, 3. and then again, it intersects both of them. This collinear region does both things at the same time. So the collinear region is when the line AB passes through 2 and is in a plane 1, 2, 3. Okay, so that's an analog of this loop momentum K being proportional to, I would say, P2 here. Yeah, I kind of changed a little bit, shifted the label here. One of the external momenta. And if the integrand has a non-zero residue on this configuration, then again, the associated integral will be IR divergent. If it has 0 residue, it will be finite. Now, if you have these two propagators in the denominator, then there would be a residue unless there is something in the numerator which vanishes on this configuration. So there is kind of a whole question about IR finite integrals. There are IR finite integrals in a simple way when you don't have these propagators. So there is nothing to start with, no divergence. And the second time is when they are present, but there is a numerator which makes them finite, even if the potential regions are present. And yeah, they will play an important role later. So let's just stop here.
Some time for questions.
Yeah, so one question was about the I epsilon prescription on in the momentum twister. Is it implicitly assumed that we have the Feynman I epsilon when we complete
there is nothing kind of new that this gives you. Yeah. So
but if I wanted to do, say, retarded propagators in momentum twister, some integrals, which would I be able to?
Yeah, there is no like new prescription that you get here. Yeah, so.
Sorry, just one more small question was the Schwartz and Matthew and Hoffy had this IR finite proposal for the N equal to 4 super Young-Mills, where they add these extra contributions to cancel the IR divergence. Is that?
Yeah, I don't know how that interacts with this. So here the object is IR divergent from the start.
Yeah, so they added these extra soft collinear contributions.
Right, so this is not included. Well, we haven't even kind of constructed the integrand using the Amplituhedron. Yeah, this is all about variables. But in the end, the thing that we would like to construct as an amplitude is IR divergent. It has the leading IR divergence given by the gamma cusp that also Johannes.
But this IR finite proposal of Matthew and Hoffy, it was Kulish Fadiev inspired.
Yeah. So the Fadiev Kulish, this kind of changes the external states. It does exactly. Not. Okay, anyway, it's not something which is part of that story. The IR finite that we would like to construct are IR finite in a different way. They are not changing the states, but they just don't have any IR divergences in the first place. Basically, doing some ratios of objects which are finite, divergent, such that the divergences are universal and they cancel. Yeah.
So it's at the level of observables, not at the amplitude that you
cancel. Right. So this is strictly for amplitudes. Of course, because of this duality with Wilson loops, we are also describing Wilson loops when the divergence become UV divergences of Wilson loops, and the amplitudes are divergent. So the Amplituhedron is for the object which is divergent. The thing that I will see if I get to in the end is the object which will be kind of finite from the start by canceling the divergences manifestly. Yeah, but not changing the external states like in the Fadiev-Kulish.
Just following up on that, of course, one could consider more general asymptotic observables, where rather than just in-out, you put some in-out, these. And those, in fact, for those, the I epsilon prescription could be important, because if you're doing some Schwinger-Keldysh kind of thing, then some places you have plus I epsilon, minus I epsilon. So you're saying here, there's nothing extra. You just have to be careful of how you do the Wick rotation when you do the integral there.
Yeah,
And
well,
some of
the
those
thing
can be
is,
IR
okay,
finite,
let me say even going farther, yeah. So the loop integration, the contour is not part of the story. Yeah, so it's really the story about the integrand itself. Now we can translate the contour from just Minkowski back to this momentum twister, but it's some complex contour. It's just a translation at that point. Yeah, here the story does not contain the contour. Now, the one thing would be do these IR finite things, so then we don't have to worry about that. The other thing, how to do the calculations, is also use some differential equation method when you also avoid the integration. So let me say that the integration itself, how it's embedded in this momentum twister space, and is there anything new, is some kind of open question. Yeah, can you gain some more, some more insight from that? But at the moment, the cases when we do use more directly the integration does not contain actually the direct integration. Yeah, it's not relied on that.
The other questions?